Hi, Alicia.
Hi, it's just me. Where's
Yeah,
everyone
it's just
else?
you. I know. Finally, one to one.
I know. Like, actually,
Yeah.
where is everyone else?
I was like, is someone gonna join today? And I was like, and then I was gonna end. I was always after like 10, 15 minutes, and then like you joined.
Uh,
Oh,
oh, there's Christina.
Christina. Hey, Christina.
Hey, good afternoon.
Hello, hello. Let me also join from my iPad. Let's see here.
Recording in progress.
Okay. Yes. So here's how we do it. We'll do 1 and 2A and then alternate between C and A and C and A and C and A. So did you have any questions or concepts you wanted to go over, Alicia?
Oh, yeah. I was wondering if we can go over the problems that you gave me. I think it was last time.
Mm-hmm. Oh, yeah, the oxidation reduction of alcohol reactions, right?
Yeah, but I was kind of confused because like
Right.
uh
Yeah, I see it. Okay.
I think you went over like the basic ideas from last time, but we didn't really go over practice problems.
Right. Yeah. So let's go over that basic idea of it and the practice problems as well. And I'll see what your thought process is. And then if you don't know how to approach it, I can show you how I think about it. And then I can give you similar ones to that. Okay.
Okay.
Here is key. Oh, is that your sister, Nikki? Christina, Nikki?
Yeah, it is. She has a midterm tomorrow. So I
Oh,
told
Mr. Turaro?
her,
For
yeah.
Ocam 1?
Yeah, for OChem 1.
Oh my gosh. Oh, Nikki, send me your syllabus and practice exam or lecture slides to this email so then we can like go over the practice problems later today. Yeah. Okay. So oxidation is the gain of bonds to oxygen, and reduction is the loss of bonds to oxygen. Right. You could also think of it in terms of hydrogen instead of oxygen. So oxidation is the loss of bonds to hydrogen, whereas reduction is the gain of bonds to hydrogen. And we have two oxidizing agents here, PCC and Jones. PCC is the weak oxidizing agent, whereas Jones is the strong oxidizing agent. And there's three kinds of alcohols that we could oxidize here: primary, secondary, and tertiary. We see that the primary alcohol here, the carbon holding the alcohol, only has one bond to oxygen right now and two bonds to hydrogen. So when we use a weak oxidizing agent on the primary alcohol, we're gonna lose one bond to hydrogen and gain another bond to oxygen. So we see that this carbon here now has two bonds to oxygen and one bond to hydrogen, which is why it's a weak oxidizing agent, because we only removed one hydrogen in exchange for another bond to oxygen, right? But when we use a strong oxidizing agent like Jones, we will get rid of two hydrogen bonds and add two more bonds to oxygen, right? Where if you look at this carbon here, this carbon now has three bonds to oxygen, which is two more than what it originally had, right? That's the hardest scenario, the primary alcohol, because it does matter what oxidizing agent you use, PCC or Jones, because that's going to give you different products, right? If you use PCC on a primary alcohol, you're going to get an aldehyde. If you use Jones on a primary alcohol, you're going to get a carboxylic acid. The secondary alcohol is easier because it does not matter if you use PCC or Jones. You're going to get the same exact product, which is the ketone, right? Because we only have one hydrogen to exchange for, um, one extra bond to oxygen, which is the ketone here. Now, the tertiary carbon here, since there's no hydrogen there, we cannot do any oxidation reaction on the tertiary alcohol. No reaction, no reaction. Did that make sense, Alicia?
Yes, it did.
Uh-huh.
Thank you.
Right. Uh-huh. So looking at the first one here, how would you go about this problem here?
Well, we said that PCC's weak.
Yep.
And then we have to look at the degree or like so that would be secondary?
Yes. Secondary because it is attached to two other carbons. That's right.
Mm-hmm.
Mhm. Which would lead us to what kind of product here?
Um uh would it be a double bond to the oxygen?
Yep, double bond to the oxygen. Which this carbon double bond oxygen here is what we call a carbonyl, and a carbonyl is an umbrella term for a lot of molecules like ketone, aldehyde, ester, carboxylic acid, anhydride, amide. Um, right, where this carbonyl here is specifically a ketone because we have two R groups flanking the carbonyl. That carbonyl is in between two R groups, making that the ketone. Right, so this is the final answer here. Oxidizing a secondary alcohol with PCC resulting in a ketone. Right.
Okay, so
Where
it just forms a double bond with the oxygen.
Yep, forms a double bond with the oxygen and gets rid of that hydrogen right there.
Okay.
Right. Because there's no more hydrogen there, we exchange that hydrogen bond to this bond with oxygen here. Okay. Okay. Next one.
Um that one be would it be a tertiary?
Yep, tertiary carbon. That's right.
And it's strong, so it's gonna have no reaction.
Yep, no reaction because this tertiary alcohol here has no hydrogen to exchange for a bond to oxygen. So we can use hydrogen,
Oh,
right?
okay. I think that conceptually makes sense now.
Yeah. Yeah, that's good. Okay.
Okay. The next one, that one would be a primary,
Right.
and then PCC, so it's weak.
Mm-hmm.
So would it form a double bond with oxygen and then still have one hydrogen left, but the other one
Mm-hmm.
would go away?
Yes, yes, right. Because this primary carbon here has two hydrogens, where we're going to get rid of only one hydrogen in exchange for this new bond to oxygen right there, right? So we don't have that one hydrogen anymore, but we still have this one hydrogen here, which I'm gonna draw out like that.
Right.
You could have also drawn it like this, which is the same thing, but it's just rotated. But it might look neater for you. But both answers are the same thing, or correct.
Okay, thank you.
Yeah, no problem. Okay, next one.
Um, that one is primary.
Yeah, so this one right here is not an alcohol at all. We have aldehyde right here.
Yeah.
Aldehyde. So we don't call an aldehyde primary, secondary, tertiary because an aldehyde is just an aldehyde. It can only be bonded to one other carbon, right? So when we use Jones, a strong oxidizing agent, we can get rid of that hydrogen right there and add another bond to oxygen, giving us what functional group?
Um, is it a ketone?
So a ketone would be a carbonyl in between two R groups, right? So this is one R group right here, but this would not be an R group, right? When we oxidize this aldehyde right here, what does that mean? What does oxidizing a molecule mean? Like you could think of it in terms of oxygen or hydrogen or both.
I think it's oxygen. I
Right.
didn't we say that uh
Yeah. So if you're thinking of in terms of oxygen, will it gain bond to oxygen when we oxidize something, or will it lose a bond to oxygen when we oxidize that thing?
gain?
Yep, gain. Right. So if we gain a bond to oxygen, we have to remove this hydrogen right here. So we're gonna add an oxygen right here, where that oxygen is gonna be the OH. Right. Because now we see that this carbon here, how many bonds to oxygen does it have?
Two.
It does have two oxygen, but this double bond here will count as two. So one, two, three. Three bonds to oxygen, right? One
Okay.
from the single bond, two from the double bond, right? What about this aldehyde right here?
Um, like how many bonds or
Yeah. How many bonds to oxygen?
three?
Yeah, so we have this oxygen right here. It's only bonded to that oxygen two times.
Okay.
Yeah, two times. So you notice how we come from two bonds to oxygen to three bonds to oxygen here?
Yeah.
That's gaining a bond to oxygen, which is oxidation. And how many bonds to hydrogen does this carbon have? How many bonds to hydrogen does this carbon have?
Is it none?
Yeah, none, zero. What about this
Okay.
hydrogen here?
One.
I mean, this carbon here. Yeah, one. One hydrogen to zero hydrogens. We lost the bond to hydrogen, which is oxidation, right? We also gained the bond to oxygen because before this carbon here had two bonds to oxygen, one, two. But when we oxidize it using Jones, it gained a bond to oxygen, one, two, three.
Oh, okay. Which is oxidation.
Yeah, oxidation is adding a bond to oxygen or removing a bond to hydrogen. Right, same thing.
Okay, that makes sense.
Right. And this functional group here is a carboxylic acid. Right. Which is more oxidized than the aldehyde. Right. Okay. Next one.
That one is a primary.
Yep, primary alcohol.
Um, and since we said it's Jones, um, it's strong, so it's going to want to, is it just make a double bond with oxygen?
Yeah, it will make a double bond to oxygen and go all the way to a carboxylic acid from a primary alcohol. Right. If we
Oh,
use
right.
a weak oxidizing agent like PCC, it will just make a double bond to oxygen and nothing else. Right. But that's a weak one. That's when we stop there. But if we use a strong one like Jones, we keep going. We add another oxygen to go to the carboxylic acid. Right. So if we use Jones right here, that primary alcohol is going to become a carboxylic acid. But if we were to use, let's say, PCC here, we are going to get this aldehyde right here. Right. So that's the difference between if we use Jones or PCC on this primary alcohol. Right. If we use Jones, we get to the carboxylic acid, the more oxidized form. If we use PCC, we get to the aldehyde, the less oxidized form.
Okay, that makes sense.
Yeah. That's good. Let me give you five more problems similar to that, and then we'll move on to 118C if Christina has questions, or Nikki's School Chem 1 class. Okay. Try these five practice problems of oxidation of alcohols and then I'll come back and check your work, and then we could go over reduction after that, like reducing back into the alcohol.
Okay, yeah, that
Yeah.
works. Thank you.
Yeah. Yeah. Let's see. Hey, Christina, did you have any questions about 118C or?
Right now we're reviewing for tomorrow's lecture the HVZ bromination and Gabriel synthesis is looking like.
Oh, right, like amino acid synthesis.
Yeah, they were using the phenylalanine phenylalanine is like one of the synthesis routes, and then like another one with com com comboed with malonic ester synthesis.
Malonic acid synthesis. Yeah, there are three ways to form it. One with the HBZ reaction, like you mentioned, the Gabriel synthesis, and have you learned about the Strecker synthesis yet?
Oh, it's on the next page, but I don't recall. Like this is my first time hearing of it.
Yeah, yeah. Okay. So let's go over the two methods: the Helvor-Zielinski reaction, HBZ reaction, and Gabriel synthesis. Right. Before we do that, though, let's determine what an amino acid is. Well, actually, I think you already know what it is because you took Miss 102.
Yeah.
So it's in the name. There's an amino group on it, and there's a carboxylic acid group on it. Right. So in neutral conditions, like if everything is neutral, this is the carboxylic acid form of the amino acid. This is the alpha carbon, and this would be the amino group. Right. And that alpha carbon right there will have a hydrogen and some random R group. Right. And you can see stereochemistry here. Most are like, I forgot, like are most amino acids D or L? D or L? Forgot. D or L amino acids. Like that's a conceptual thing that you might have to know. I'll have to review the slides and to recheck. But all of these highlighted portions right here are going to be shared by all amino acids. All amino acids will have a carboxylic acid, an amino group, an alpha carbon, and a alpha hydrogen, right?
It says most have the S configuration.
Oh yeah, so
that's different from D and L.
right. That's different than D and L. I was thinking about sugars. Sugars. Most sugars are D sugars. Most amino acids are S configuration.
Okay. Yeah.
Most amino acids are S because the chiral sensor would be this alpha carbon, where most would be S when we assign the priority group, right? Where this R group here represents a side chain, a functional group, and it's different for 20 amino acids. Like it could be a methyl group, it could be an isopropyl group, it could be a thiol group, it could be an aromatic group like tyrosine with the benzene and alcohol. Like, it's a variable group, like a side chain, right? In physiological pH, which is around 7.2 to 7.4. The amino acid would have this form here where the amino group is protonated and then the carboxylic acid group is deprotonated. Right. And the reason why is because let's just say at a very low pH, like at a pH of 0, every single group is going to get protonated because when you think of pH, think about the environment. The environment is very acidic right now. There's a lot of hydrogen ions floating around, which is going to protonate every single group of the amino acid, giving us this configuration here, right? Where the carboxylic acid is protonated, the amino group is protonated. The carboxylic acid pKa is around 2. The amino hydrogen's pKa is around 9 to 10. Right? Let's say 10, but it's going to be 9 point something, most likely. Right.
But it's never going to exist in that. Well, I know it's never going to exist in that state, like physiologically, because the body is super regulated.
Right,
But
super
will we
regulated.
be seeing it in that state, like for his problems?
Yeah. Because he would say, what would the structure look like at a pH of 0, at a pH of 1?
Okay.
Yeah, and then it would look like this. And then there's something called a pH elevator that I like to use to like predict the structure of the amino acid, depending on what pH it is, like pH 0, pH 1, 2, 3, 4, 5, 6, 7, all the way to 14, and how that would affect the structure here, right? Where some R groups, there's a lot of properties to the different R groups, right? There's like aliphatic ones, there's polar ones, non-polar ones, acidic ones, basic ones. Those acidic and basic ones right there, they have pKa as well, because we can deprotonate.
So like aspartate and glutamate would both be like a little bit more acidic in comparison to like their amino asparagine glutamine counterparts.
Yep.
Okay.
Right. And lysine and all those like other basic ones. Right.
Okay.
That's good. Yeah. And then we'll go over that later. Like that's more biochem related, which you're familiar with. But let's go over like how to make amino acids in the first place. Right. Preparation of amino acids. So the first method we're going to talk about is the Helmholtz-Zielinski reaction, HBZ reaction. Zielinski reaction, HBZ. And you seen this reaction before in the chapter 19, the carboxylic acid unit, right? Because whenever you have any kind of carboxylic acid with an alpha carbon, and you react that with these reagents, Br2, trace PBr3, what would that do to this carboxylic acid here and its alpha carbon?
Wouldn't it
It's okay if you forgot. I could just tell you too.
attach the bromine at the alpha position?
Yep. It would attach the bromine to the alpha position, the alpha carbon. That's right. Right. So you know that this is the carboxyl group, this is the alpha carbon, and this Br here is a good leaving group. So to convert that good leaving group into, let's say, an amine group, to get the amino acid, we could use ammonia. These are the reagents that I saw when I took the class. Water at room temp, and it's going to take like 4 days to do this. An SN2 reaction, right? Where the ammonia here is going to attack that carbon, kick out the bromine to substitute that bromine with the amino group right there, right? Where this is the carboxyl group, this is the amino group, and this is the alpha carbon right there. And then the R group here is already given to you in the reactant, right? So this HBZ reaction here will form an amino acid, but you like if they give you the carboxylic acid to begin with, you can't change the R group, right? The R group is already given to you with the carboxylic acid. There is another reaction that you get to choose what the R group is, which is the Gabriel synthesis, right? Gabriel synthesis will allow you to pick what R group you want on the amino acid, right? Think of the HBZ reaction as just converting a carboxylic acid into an amino acid by adding like an amino group alpha to it. But to do that, we have to put a good leaving group there first, which is the HBZ reaction, bromine. And then once we do that, we do SN2 to substitute that bromine with the amino group, which gives us our amino acid right there. Right. Okay. Now, the other method to form amino acid is the Gabriel synthesis, which I think you learned this in chapter, the amine chapter, I forgot, 23. Right. So we're going to start with something called the phthalic acid. Phthalic acid, which has a unique, distinct structure, a benzene, with 2 carboxylic acids ortho to each other, like this. All right. And if we were to react those 2 carboxylic acids ortho to each other with ammonia and high heat, like 300 degrees Celsius, do you remember what that would do with these carboxylic acids here? It's okay if you don't remember.
It gives An imide? An imide?
Yep. An amide, a cyclic amide, closing the ring like that. That's right. And water would leave here as well in the mechanism. Like if you were to go through the whole mechanism, water is going to be the leaving group that leaves.
Mhm.
Right. That's good. And this is what we call the phthalimide. Phthalimide. Right. That's nice. Now, this hydrogen here of the phthalimide is acidic. Right. Because when we deprotonate it, giving that nitrogen a negative charge, this negative
Mhm.
charge here is very stabilized. Right. Can you think of a reason why this is very stable, this negative charge?
Is it because it can do resonance with the carboxylic acids and okay, yeah.
Yeah, the carbonyls. It could do resonance with the carbonyls.
With the carbonyls, yeah.
Yeah, the carbon double bond oxygens, right? So let's deprotonate it, and the common base that you'll see to deprotonate it is going to be K2CO3, right? The carbonate ion. Like that base is going to come in, grab that hydrogen, and give that nitrogen a negative charge.
Is LDA another strong base that we could use, or just
LDA is another strong base we could use, but LDA is like really, really strong. It's gonna like rip off that hydrogen and give that nitrogen a negative charge. Yeah, LDA is actually a base you could use as well. Yeah, LDA.
because
CO.
I know that for the midterm that we had, he for the reducing agent, like I used too strong of one of the reducing agents, and they were like no points for that one.
Oh,
Yeah.
you took up at midterm 1, right? Like with the reducing agents.
Or the midterm two. Yeah, I used like PCC.
Hmm.
No, PD2 to reduce it. And it was like, no, you're supposed to use FeHCl as the
Oh,
reducing agent.
like with the benzene like this, and then you wanted to reduce NO2 into NH2.
Mm-hmm.
And they said you couldn't use H2PDC.
Yeah, they said it was too strong.
Oh, okay. That's different than how I learned it, because H2PDC does work with this reaction. Right.
I want to say because it had like another
Oh,
group on it.
right. If it had an alkene
Mm-hmm.
like this, then this would not work. H2PDC would not work. Right? Because it would over reduce the alkene and the NO2. Right? So we won't use
Mm-hmm.
H2PDC. We're going to use iron HCl. Iron HCl, which would avoid reducing the alkene. If we were to use H2PDC, this is what we would get instead. We're going to reduce the alkene into an alkane and the NO2 into NH2. Right. So this H2PDC is a strong reducing agent because it would over reduce the whole molecule. But we want to keep our alkene. So we want to use a weaker reducing agent like iron HCl there. Right. But if the alkene wasn't there, then you could use HCl, H2PDC, iron HCl.
I think it's because there was a carboxylic acid on it. That's what they were saying. That if
Oh,
you had a carboxylic acid on the benzene ring meta to the NO2,
uh-huh.
that you had to use FeHCl, not H2PDC.
H2PDC. Oh, interesting. Yeah.
And I thought that you really can't reduce, I mean,
Yeah.
would H2PDC reduce the carboxylic acid? Is that why we wouldn't be allowed to use H2?
H2PDC. Yeah, I can see why, because H2PDC is a stronger reducing agent than iron HCl, and carboxylic acid here can be reduced down to like an aldehyde or a primary alcohol.
Okay, that makes sense.
Primary alcohol. Right. So yeah, that makes sense. Yeah. Okay. So once we deprotonate this phthalimide right here, we're gonna get this negative charge on the nitrogen, which is gonna be our nucleophile. And then um this nucleophile right here, the nitrogen, we're gonna like attach a very unique electrophile to it, right? It's gonna be a diester, a beta diester. So here, I'll show you what I mean by that.
Mhm.
It's gonna be that good leaving group right there, and that good leaving group is alpha to 2 carbonyls, where those 2 carbonyls are esters, like this,
Okay.
right? Where if we were to attack this carbon here and kick out the bromine, we are going to get this structure here. I'm just going to do the reaction for you, show you it, and then show you like the purpose of each reaction of why we did that, why we added this
Mhm.
specific reagent, right? And that's going to add this group to the phthalimide. Okay. So now I'm already going to show you what our amino acid group is going to be. So this is going to be the amino group of the amino acid, and this ester here is going to be our carboxylic acid group right here, where our alpha carbon is going to be that alpha carbon right there in between
Mhm.
the amino group and the carboxylic acid, right? So now, if we want to add a specific R group at the alpha carbon, do you
Mhm.
remember a way that we could do that? Like if there's an alpha hydrogen right here that's acidic, like do you remember a way that we could alpha alkylate a molecule?
Mm. Can't that nucleophile wait. No, I don't remember.
Yeah. It's okay. So if we want to make this alpha carbon a nucleophile, right, negative charge to attack, let's say, some kind of halocane, to add some kind of random R group that we want, to
Mhm.
make that alpha carbon a negative charge, we have to deprotonate the alpha carbon. We have to take that alpha hydrogen and give that alpha carbon a negative charge.
Using a base, right?
Yeah, we have to use a base. Yes. We have to use a base to deprotonate that alpha hydrogen to give the alpha carbon a negative charge. And the base that we're going to use here has to be NaOR, where the OR group has to match the OR group of the ester.
Okay, so that way we don't get a transesterification as to match.
Yes, because
Okay.
if we have a different OR group, we're going to have transesterification, right?
Okay, that makes
Which is
sense.
going to substitute that OR group with this OR group here, whatever that OR group is,
Mhm.
right? If we use NaOH in water, that's going to do hydrolysis. It's going to convert these esters into carboxylic acids, carboxylates, right? But we don't
Mhm.
want to do that. We don't want to do transesterification or hydrolysis. We want to deprotonate this alpha hydrogen, so we have to use NaOR, where the OR group matches with the ester, to deprotonate that hydrogen and give that alpha carbon a negative charge. Right. Now, once this alpha carbon has a negative charge, that is now our nucleophile. And once we have the nucleophile right here on the alpha carbon, we could add any electrophile we want, like any R group we want.
Mhm.
Let's say we want to add a isopropyl group. So to do that, we have to give that isopropyl group like that, which this
Mhm.
carbon here, the star, is going to attack this dot for SN2 reaction, picking out this good leaving group here, SN2 reaction, right? And then that's going to give us this intermediate here. Okay. So star, new bond between star and dot. Dot is attached to 2 methyl groups.
Mhm.
1, 2, new bond. Okay, so now we almost have our amino acid. We have our amino group here, our R group here, and then our soon to be carboxylic acids here.
Mhm.
The final step here is the one of the final steps here is to use acid, water, and heat, H2O plus, water, and heat. And what that's gonna do is it's gonna do hydrolysis, right? Convert these amides into um the carboxylic acid. So do you remember when we
Okay,
have
yeah. How we
any
started.
derivatives? Yeah, that's gonna convert that back into the carboxylic acid and then kick out that amino group like that. How we started, right? Get that carboxylic acid like that. That's right. Um, how we started. Get this amino group right here, but because we're in acidic conditions, the amino group is gonna get protonated by the acid, right?
Mhm.
And then these esters here, they're gonna get converted into carboxylic acid because we're doing hydrolysis here. Hydrolysis of all derivatives. right? But this is not our final answer here because we have a sneaky reagent here, which is heat, and we have a beta carbonyl acid, right? Because we see that if you look at one of the carboxylic acids here, beta to that carboxylic acid is another carbonyl reacting with heat. So that is a sneaky reaction called decarboxylation, right? Where one of the carboxylic acids is going to disappear and get spitted off as CO2.
Okay, yeah.
Yep. Right.
So,
So then we get that carboxylic acid right there. Right. But at physiological pH, let's use some kind of base like NaOH in water to get the amino acid in its regular form, where the carboxylic acid is deprotonated and then the amino group is protonated. Right. This is like the amino acid in physiological pH.
Okay.
Right. And this is the R group that we added right there. Right. Okay. So to recap this whole Gabriel synthesis, to create the amino acid, you can start with the phthalic acid or phthalimide, depending on what the problem gives you. Let's say we start with the phthalic acid. We convert that phthalic acid to phthalimide by forming an amide, right? Chapter 19 reaction, we have carboxylic acids here. React that with an amine with high heat, form the amide here. Once we have this amide with the acidic H, we use a base like K2CO3 to deprotonate it to get this nucleophile there on the nitrogen, right? This nitrogen right here is going to be the nitrogen of the amino group, the NH2 of the amino group, right? And then once we have this nucleophile here, we have to add this specific electrophile, the beta diester here, because we want them to be beta to each other to allow us to do decarboxylation later on in the mechanism.
Yeah, that makes perfect sense.
Right. And the reason why we don't use beta dioic acid like this is because if we put beta dioic acid, OH, and we try to deprotonate this alpha hydrogen to make that nucleophilic, that would not be the most acidic hydrogen. The most acidic hydrogen would be the hydrogens of the carboxylic acid.
Okay, so you need it to be the
Ester.
diester because it, okay, that makes sense.
Diester. We want it to be the diester to avoid making a more acidic hydrogen than the alpha hydrogen here. Right. We want that to be the most acidic hydrogen to make that alpha carbon nucleophilic. And we want that to be nucleophilic because that's the alpha carbon that will attack some random R group we want to become the R group of the amino acid. Right. Which is this R group here. And then once we have this complex, then we hydrolyze everything to spit off a phthalic acid. We could spit off the alcohols of the ester that got kicked out. But this won't stop here because we have a beta carbonyl acid reacting with heat, which is going to do decarboxylation, spit off one of the carboxylic acids into CO2 to get that amino acid right there, the protonated amino acid, because we are still in acidic conditions.
I also had one other question on the midterm.
Yeah.
What's the difference between intra-adol condensation and then Deichmann condensation, or intra-Claisen condensation? I know Claisen and Deichmann are the same, but I put intra-adol condensation as the reaction name instead of Deichmann condensation. I was just wondering, like, what makes them different?
Deichmann condensation is the intramolecular, is another way of saying intramolecular Claisen condensation. Yeah, that's a good question because a lot of students get confused and mixed up with these different reactions, like Claisen aldol, Deichmann, Michael addition, Robinson annihilation, like the enolate chapter reactions. And I'm going to show you a table that I use, and I know in the top of my head that I keep these reactions straight. Like this is the table I think about when I think about these reactions. And then you're asking about the difference between that versus aldol. Yeah, intramolecular aldol condensation. Right here. Aldol. Okay. So the difference here is that Deichmann condensation is a Kaizen condensation, which is going to be completely different than an aldol reaction, aldol condensation, right? Aldol condensation, let's say. Right, because aldol, there's two reactions to it. There's aldol addition. That's the one when you do not have heat, no heat, and there's aldol condensation. When you do have heat and you go all the way down to the aldol condensation product. Right, but a lot of professors, they tend to skip over the heat and they just assume heat. So even though if you don't see heat, they just go all the way to the aldol condensation. Like I think Farhad does that. Like Farhad assumes for aldol condensation. Right. Okay, so there's going to be, let's say, different reactions here. Aldol, and I'm gonna like separate that into aldol addition and condensation. I'll split that later on in this table. There's Tizen. There's Michael.
Isn't Michael addition and Robinson annulation together placing or no?
Yeah, so Robinson annulation has two steps to it. Michael addition is the first step of Robinson annulation. The second step is intramolecular aldol condensation.
Okay, that's why I'm getting confused because like they're all like different pieces.
Yeah, they're different pieces, like, and they're very similar. The mechanism is very similar. Right? It's like a step intramolecular aldol. That's why I got overwhelmed at the end of 118B because like all these reactions were so similar and I couldn't like separate them. Like they're so similar. I kept mixing these up. Condensation, right? Because when you have an aldol condensation, there's three different types. There's self-aldol, there's mixed aldol, and there's intramolecular aldol.
Yeah.
But for Robinson annulation, the first step is Michael addition. The second step is specifically intramolecular aldol, not a self-aldol, not a mixed aldol condensation, right? So I'm just gonna do these three reactions: aldol, Claisen, and Michael, aka conjugate addition. Conjugate addition. Okay, and then I'm gonna categorize them by nucleophile, by electrophile, and by the product they form. Okay. And this is gonna be good for 118B at the end of 118B when you take it, Elysia. Like, in my opinion, the end of 118B was like the and the beginning of 118C was the toughest for me. Because beginning of 118C, there was also a lot of reactions to keep track of, like the carboxylic acids, derivatives, and all those reactions like reduction, organometallics, hydrolysis, interconverting between them. Yeah. But there's a pattern to it. Like there's a lot of patterns to it. And if you make tables and charts, then it will like keep everything organized and like a big whiteboard and everything. So it's okay. It's okay. You got it, Elysia. You have Helix, right? Next quarter for 118B, you register for Helix.
Yeah.
Yeah, that's good. That's good. Yeah. Okay. So Aldo, Claisen, and Michael addition or conjugate addition, all the nucleophiles are going to be the same. It's going to be an enolate ion, more specifically the alpha carbon of the enolate ion. So if I were to give you an example of what I mean by that is that if you have this enolate ion here, the nucleophile would be that alpha carbon right there, not the O minus. It looks like the nucleophile was the O minus because the negative charge is directly on the oxygen, but it's not because when we do resonance here, we're gonna get this resonance structure where the negative charge is on the carbon, and we know that the negative charge on the carbon is less stable than the negative charge on the oxygen. And because the negative charge on the oxygen is less stable, it is more reactive, more nucleophilic. So our star here is that alpha carbon, the alpha carbon of the enolate ion. That's going to be the same nucleophile for all of these reactions: aldol, Claisen, and Michael addition or conjugate addition. Same nucleophile. What distinguishes these reactions together is the electrophile. The electrophile for an aldol is a carbonyl carbon of an aldehyde, most likely, or a ketone if it's intramolecular. Right, so our dot or electrophile here is going to be the carbonyl carbon of an aldehyde, most likely, or if it's intramolecular aldol, it could also be a ketone.
Mhm.
The electrophile, yeah, a question?
No, you're good, you're good.
Yeah, electrophile for Claisen is going to be a carbonyl carbon of an ester. Right, so an example would be something like this, where the OR group of the ester is going to be the leaving group in the mechanism, right? But the electrophile is the carbonyl carbon of an ester, or Claisen. For microaddition, the electrophile is going to be the beta carbon of an alpha beta unsaturated carbonyl. So you know that you're going to have a microaddition whenever you have a structure like this, when you have an alkene next to a carbonyl. And if this is the carbonyl carbon, this is the alpha carbon, there's a beta carbon right there. And we see that there's a double bond between the alpha and beta carbon, or an unsaturation between them, which is why we call this an alpha beta unsaturated carbonyl. There's two possible electrophiles here, the carbonyl carbon or the beta carbon. The beta carbon is the better electrophile, the stronger electrophile, because when we draw out the resonance structure of that alpha beta carbonyl, alpha beta unsaturated carbonyl, we see that there is a full-on positive charge on that beta carbon, right? Which is why our electrophile here is the beta carbon of the alpha beta unsaturated carbonyl. Hard nucleophiles or irreversible nucleophiles would attack that carbonyl carbon, like organometallics or reducing agents. But in this enolate chemistry, if our nucleophile is an enolate ion, the electrophile is always going to be the beta carbon of the enon, right? The product for aldol, if it's aldol addition, which is no heat, it's an aldol, right? Meaning that the product has an alcohol beta to a carbonyl, most likely an aldehyde. If we do condensation with heat, we're going to get the alpha beta unsaturated carbonyl, right? Which looks like this. And in Fahrenheit class, just assume heat and go all the way to the aldol condensation product to get this alpha beta unsaturated carbonyl. Or Claisen, it's going to be a 1,3 dicarbonyl. Right, where the most common 1,3 dicarbonyl is going to be a beta keto ester. The reason why I say 1,3 dicarbonyl is because not all Claisen would give a beta keto ester, especially intramolecular Claisen, right? But most Claisen condensations would give a beta keto ester, but all Claisen would give a 1,3 dicarbonyl, which would look something like this. Right, where this is the carbonyl carbon of the ester, this is the alpha carbon, this is the beta carbon. And at the beta carbon, we see ketone, which is why we call this a beta keto ester, a ketone beta to the ester here. Okay, the product of a microaddition is going to be 1,5 dicarbonyl. So we're going to have two carbonyls, that's why it's the dicarbonyl there, that have a 1,5 relationship with each other. So if this is your 1, 2, 3, 4, 5, we see that these two carbonyls here have a 1,5 relationship with each other. And they tend to proceed to do intramolecular aldol condensation
Would
for
it be a 5-member ring?
wrong
Trying to
and
think.
yeah, so this right here, the way I numbered it, it looks like I'm closing the ring here, but I'm not closing the ring. We won't make a 5-membered ring because the nucleophile has to be an alpha carbon. right? One of these carbons here is going to be the electrophile because it's positively charged. So let's say that
Mhm.
this is our electrophile right here, that carbon and carbon right there.
Mhm.
Our nucleophile has to be either this alpha carbon or this alpha carbon here.
Oh, it's not the alcohol, or
No, it's
not the oxygen.
carbonyl. Yeah, it's not the oxygen, right? Not the oxygen. It's the alpha carbon. That's the nucleophile, right? Because we're
It's
still in
always going to be the further one way away
uh-huh.
because to avoid ring strain, right?
Yeah, right. Because the further one is going to make the 6-membered ring, right? One,
Mhm.
2, 3, 4, 5, 6. The closer one right here would make a 1, 2, 3, 4-membered ring. That's too much ring strain, too much bond angle strain. That's right. That's
Mhm.
right. So if you reach this 1,5 dicarbonyl and you're still in basic conditions, you would want to deprotonate the furthest isolated alpha hydrogen to give that alpha carbon a negative charge, which would attack the other carbonyl on the other end to make the most stable ring, the 6-membered ring.
So this one would give basically a cyclohexane with a ketone off of it and then a methyl group, right?
And also a carbonyl as well. It will give us this alpha beta unsaturated carbonyl because we're doing an intramolecular aldol condensation. So it will give us a cyclic uh, um, alpha beta unsaturated carbonyl, something that would look something like this, like that.
Okay. Was there methyl as well or no?
Yeah, there would be methyl. Like if this is 1, 2, 3, 4, 5, 6. This is 1, the star. This is 6, the dot. The dot.
Mhm.
This is the double bond between the star and dot.
Mhm.
2 had a carbonyl, and a 6 has a methyl, which is this methyl right there.
Okay, that makes sense.
Right. That's good. Yeah. So that's how I keep these enolate reactions straight in my head and the differences between them. And I just like look at it over and over and use it when you practice. Make your own chart, make your own connections. Like this is just what I picked up when I was doing practice problems and like mechanisms a lot about these reactions.
No, this actually helped so much because yeah, they all kind of look the same. So like you were saying, this chart is definitely I want to be using it.
Yeah, that's so good. Yeah. Okay. Hey Nikki, did you send? Oh yes, you did right here. Okay, let me open that up and open this right here, midterm to practice. Did you have a specific question that you wanted to go over or a specific problem that you needed help in? Over W, yes. W. Oh, it's probably not this one, huh? It's probably a different one. Let's see. This one? W. A.
Hi, could you hear me?
Yes, I can hear you. Hi.
Okay, awesome. Hi, sorry, I'm in like a quiet library, so I went out to the hall really quickly.
Huh? Yeah. Oh well, library thing. At this time, you're so dedicated. What the heck? Wait, what time does the library close?
2 a.m.
2 a.m. Oh my God. What the heck? Is it always like that, like throughout the whole quarter or your semester?
No, so on like Saturdays it'll close at 10, and then I think every other day it closes at 2 a.m. But
Oh,
on like Sundays though, it doesn't open until like 1 p.m.
yeah. Is it UC Berkeley library?
Yes.
UC Berkeley. Oh my gosh. Yeah. Do you go there often? Like every day study? Oh my gosh.
When when it's midterms, I usually go for like the 4 days prior all day.
Oh my God. Wait, what's your major at UC Berkeley?
It's integrated bio.
Integrated bio. I
But
see. I see.
I
Uh-huh.
want to switch to OK or just chem because I think
Yeah.
it's a bit more enjoyable, at least the way
Oh.
they teach it here.
Uh-huh. Yeah. So you're the opposite of Christina. Christina's more of a bio person. You're more of a chem person.
Yeah.
That's good. That's good. Uh-huh.
Um, I'm kind of so there's a few things that I'm kind of having like struggle with. So I have my midterm tomorrow,
Yeah.
and
Mm-hmm.
I'm kind of struggling with like E2 versus E1. And then like
Yes.
SN1 versus SN2, like all of those four, I'm kind of confused on. I get it, but like the specific conditions, I kind of get a little mixed up on.
Right. I can go over the differences with you on SN2, SN1, E1, E2. It's like it's like a really big concept, big reaction. But there are tips and tricks I look out for. I'll just show you my thought process because I don't think I have time to explain everything conceptually, like what each reaction means.
Yeah.
But
I get I know the overview of all of them, but it's like the specific conditions is what I kind of sometimes get mixed
Uh-huh.
up on.
Right. So the conditions that we always have to look out for is what type of substrate do we have, right? Like if we have a methyl substrate or a primary substrate or a secondary
Okay.
substrate or tertiary
Or
substrate,
tertiary. Okay,
right?
yeah.
Uh-huh. And then the other important factor we have to look at is what type of nucleophile and base do we have?
Okay.
Well, and base. And there's four types that I look out for. We can either have a weak base, strong nucleophile, a weak base, weak nucleophile, or a strong base, strong nucleophile. Right?
Oh, okay.
Yes. And
I
then
think that's what I'm getting tripped on because I feel like some I know some are weak and some are strong, but I didn't know like they can be like overlapping on both sides.
right, there's a lot of overlap and a lot of confusing reagents because when you're first learning these reactions, they throw a lot of reagents at you and they expect you to know what reagent does, like what reaction it does. Right.
Right.
But also like it also depends on the substrate because if you have a strong base strong nucleophile, it will not always be an E2. It will most likely be an E2 reaction, but it would not always be an E2, right? Because if
Okay.
it's a primary substrate, it would do SN2, but if it's secondary tertiary, it would do E2. And there's this table that
Okay.
I want to show you that helps me out a lot. Like when I was learning this reaction, I referred to that table a lot, and then I kept doing it until I was able to not look at the table and just do more reactions, like predict the product without looking at the table, right?
Okay.
Um, but the easiest list to remember here is the weak base, weak nucleophile. So if it's weak, everything is going to be neutral, and it's only two that you have to worry about here: water and alcohol. Water, H2O, and alcohol, ROH, neutral,
Okay.
right? And these are weak base, weak nucleophiles because everything is neutral. There's no full negative charge, and then if everything is neutral, it's super stable, super happy. Right. And because it's super
Okay.
happy, it is super stable. It doesn't want to react with anything. That's why it's very weak, base weak nucleophile, because it's not reactive at all. Right.
Okay.
And these tend to do SN1 and E1 reactions. They go together, SN1 and E1 reactions.
Right, because they'll have the positive carbon cation.
Yes, positive carbocation intermediate after the leaving it loose phase. That's right. That's right. SN1, E1, they always have that carbocation intermediate. And then whenever you have that carbocation intermediate, you always have to watch out for a sneaky step. Watch out for hydrate shift or alkyl shift. Most likely,
Okay. Oh, okay.
right? Right, because we want to be able to react with the most stable carbocation intermediate.
Which would be like the tertiary, right?
Yes, for now, tertiary. Methyl is the least stable. Primary is the second least stable. Secondary, and then tertiary is the most stable that you learned, right?
Right.
And there is a factor that describes all of this, which is hyperconjugation.
Right. Okay.
Yeah, and I think of it as like friends. This positive charge here is missing electrons, so the more friends it has, the more stable it is. The less friends it has, like this carbon here has no R groups, it's more lonely, it's sad, it's unstable. The more friends it has, the less lonely it is, the more happy it is, the more stable it is.
Okay.
Right? You can think
Gotcha.
of it like that. Right. So now if you see a strong base, strong nucleophile, that's gonna be most likely when you see a negative charge, a full negative charge on an oxygen atom or a nitrogen atom. So examples, hydroxide ion, O minus ion, alkoxide ion, NH2 minus, RNH minus, R2NH minus, like any negative charge on an oxygen or nitrogen, like that.
Okay.
Right? And they tend to do E2 reactions on secondary and tertiary substrates.
Okay.
Right. SN1, E1, because they want to make the more stable carbocation, they will only work on secondary or tertiary substrates as well. Primary substrates would not work because we can't make a primary carbocation, too unstable to exist.
Right. Okay.
So that's why it's gonna be no reaction, but you'll see that in the table when I show you. And there's gonna be two types of strong base, strong nucleophiles. There's gonna be called a small or unhindered base, and then there's gonna be a bulky
So this
base.
is based on sterics, right?
Yeah,
Okay.
it's based on sterics, right? And then the most common one you see is turbutoxide, something like this.
Yeah. Okay.
CONA or K. And the other one that you'll see is LDA, which looks like this, because it's very bulky, very sterically hindered. But small bases are like OH minuses, ethoxides. Even this right here is considered a small unhindered base. It looks very bulky, but that's unhindered, right? Because what makes a base bulky or hindered is the first carbon attached to the O minus, that first carbon right there. If it has like more than one branch, like let's say more than like at least two branches, it's bulky, right? Like we see that carbon there has two branches, so that is automatically bulky. But this
Okay.
one carbon here only has one branch, so
Okay.
that's small because it just like goes away in the periphery, in the equator. It just goes away. It
Okay.
doesn't interfere with the reaction.
Okay. That makes sense.
Yep. And then the bulky base will likely to do Hoffman E2. I don't know if you learned about Hoffman or Zaitsev yet. And the small unhindered one
Not yet, but we have learned about E2 and all of that.
Zaitsev. Okay, yeah. So if you go to our next office hours, or like I could go over this with you too. But that's what it is. And everything else is gonna be weak base strong nucleophiles, like the CN minus, N3 minus, SH minus, even neutral amines, right? Not negative charge amines, because if it's negative charge, then that would be a strong base. And all of these right here would do SN2,
Okay.
right? But SN2, they only work on primary or secondary substrates, not tertiary, because SN2 prefer less sterically hindered substrates, right? Tertiary is too sterically hindered. With steric hindrance.
Okay. Gotcha.
SN2, that's a backside attack. It wants to like reach the electrophile with more space. Right?
Okay.
Okay, so those are the two most important factors I look for. But let me show you that table right now that I was talking about. And then I'll send this to my notes, which is gonna be on school if you're in it, and then you could access the notes there as well. Right.
Okay.
Let's see. This one, 118A, magic table, SN2, SN1, E1, E2, magic table, this one. And there's specific notes for each reaction and practice examples for you.
Oh my God, this is perfect. My midterm, we're allowed 4 pages of cheat sheets, so I'm gonna write this all down.
Wait, four like 4 printer papers, front and back?
Like 2 front and back, or just 4 individual.
Oh my God.
But they're really, really hard, the midterms.
Oh yeah, I know. Oh my gosh.
I always feel like if they allow cheat sheets, it's gonna be worse than what you think.
How has the average? Wait, no, how has the averages been for your other birthday classes been so far?
They're kind of like in their 50s, I think. They're usually in their 50s, but they say that they never really curve here.
I know,
Like
that's what I
ever.
heard too. That's crazy. 50 average, no curve.
Yeah, it's really rough.
What
But
the heck?
for our chem class, I heard that people did pretty bad for the first midterm, for the first OChem one, but she
Yeah.
won't tell us the averages.
Oh my God.
But she
It's
doesn't
like,
want us to like compete against each other, so she's like, there's no curve, so it doesn't matter.
oh my God. Is it like a grade deflation thing there? Like, is it true?
Yeah,
Oh,
yes,
that is
yes,
true.
definitely. Yeah.
Crazy.
At least for the lower divs, it's true.
Yeah. Oh my God. It's rough out there.
It is. It really but it's okay.
Yeah. Yeah.
So this is a magical chart for E2 versus SN1 versus SN2. Okay.
Yeah, right. Like, and the type of substrate is here: methyl, primary unhindered, primary hindered, secondary, tertiary. What type of base is strong nucleophile you have? Small, bulky, and the type of reaction is gonna deal, or no reaction at all.
Okay, awesome. Oh my God, this is perfect. I'm gonna write this all down.
Yes. This table is very good, and then you can do examples here to reinforce it.
Okay.
It's good.
This is gonna be like game changing. Okay, thank you so much.
Yeah, no problem. I got this from my tutor when I took the class, so this is very goated.
Oh, okay, yeah.
Yeah.
I'm grateful that you're passing it along.
Yeah, yeah.
Um, could I also ask you, what's your like thought
Mhm.
process on like multi-step synthesis?
Yes.
I I think I sent worksheet W, and they
Uh-huh.
had some of these, and it's basically like a lot of blank boxes. This one
Right.
looks like E. Yeah, this is E, and then
Yeah, so for multi-step synthesis, they give you the reactant and the products, right? But they don't give you the reactions in between them.
kinda they give you like I don't did I send you the worksheet? Did I send you it? I
I
say that
think
because like it's W. Yeah, post
W.
lecture W.
Let's see here. Oh, this one?
Yeah, so they kinda like
Mhm.
how would you go about this?
Yeah. There is a whole thought process on this. Like retrosynthesis, going backwards, cutting bonds, disconnecting them, forgetting what the nucleophile electrophile is. Um, but how I go about this is that I look at the reactant molecule and the product molecule, find out what
Okay.
my differences are,
Okay.
and find out. Well, the first thing is find out what the similarities are. Like what are the similarities?
Right, okay. That
And
way
then
that's like the same thing throughout the whole thing
yeah,
time.
same thing throughout the whole time, right? Which we see is the benzene ring with the C with the carbon and then the OH right there. That's the same thing, right?
Right, okay.
And then I see what the new groups are, what changed, what is the differences between them, which is the ethyl group and the D,
Okay.
right? And then once I see the new groups there, I ask myself what kind of reactions would add those new groups. And if you see any new R group, any new hydrocarbon chain, then that's going to be organometallic reaction, like a Grignard reagent, Grignard reaction.
Okay, like organium, lithium, or
Yes,
something like that. Okay.
organolithium. Yeah, organolithium or Grignard reagent. Yes,
Okay.
organometallic. And then you just ask yourself like what are the reactants and products that would do that reaction, and then like try to get that, go backwards or forwards, try to meet in the middle, and more disconnections. Like if I had more time, I would show you like step by step process, but
No,
that's
no, yeah,
how I
don't
would do
worry.
it. Right,
Next
like
time.
yeah, next time, yeah, yeah. So before your next
All right.
midterm, for sure, and final.
Thank you so much.
Uh-huh. Yeah, no problem. Right. Uh-huh. So I'll end off office hours here by going over the practice sums I gave you earlier, Elysia. Were you able to do those? These ones here? Oh, you sent it to Discord. Oh yeah, let me go check. Let me go check. Yeah, I could send you the notes to the sessions for today's office hours sessions after the session to your email that you sent me. And also if you want to join future office hours, there's this Google platform that maybe Christina could send you to join where you could access all the Zoom links, all the notes and everything.
Yeah, I'll share it all with her. I
Yeah.
just told her to join because I was like, "Hey, you're gonna be happy you joined. Just he's really good."
Yeah,
But
yeah. Thank you.
thank you,
For showing Christina.
thank you so much, Brian. I appreciate it.
Yeah, no problem, Christina.
Hello? Can you hear me?
Yeah, oh, I can hear you, Alicia.
Okay, yeah, my mic wasn't working, so I
Uh-huh.
rejoined.
Yeah, no worries, no worries. I just imported it to the my file. I'm gonna share my screen again, and I saw you sent the PDF. Thank you for that.
I know.
Yeah.
Yeah.
Okay, so this one here. Yes, you got it. This one. Yes, you got it. Carboxylic acid. This one. Yes, you got it. Aldehyde. This one. Yes, carboxylic acid. This one. So this one is a strong oxidizing agent, primary alcohol. We want to get the um, carboxylic acid. So this is the carbon here holding the alcohol, which is going to be that carbon. This
Oh,
would be the
yeah, I forgot the
intermediate.
OH. I don't know what happened to the H.
Right, right. instead of that, it's gonna keep going further, oxidize to become OH, the more oxidized
Uh,
form, right? It gets to this intermediate first, but then later it gets to the more oxidized form because we're using a strong oxidizing agent here.
okay. Yeah, I think I accidentally just forgot to put the O
Uh-huh.
there.
Oh,
But yeah.
but you had your O in your head, right? Like when you were doing this.
Yeah, I probably
Yeah.
did. I just didn't put it on.
Yeah, but you got it. You got it, Alicia.
Yay.
Yeah. And then
Okay. Thank you
in
so
tomorrow's
much.
office hours, I'm gonna go over the reduction reactions with you at the beginning
Mm-hmm.
first, and then also text me what you're going over right now so that I could like give you a brief overview of that concept and practice problems. So then I could like go over that with you and proceed with the 118A.
Okay.
Embrace
Yeah,
miss.
I don't have your number, but I guess I could put through Discord,
Yeah.
or what's
You can send,
easier for you?
right. You can send it to Discord, like the your questions and what you're learning. Uh-huh.
Okay, yeah, I think we just started ethers, and I'm a bit behind on lecture notes, so yeah, I'm definitely gonna catch on over break for sure.
Yes.
And like tonight, I got myself a whole pack of Celsius.
Celsius. Oh my God, that's my favorite
Yeah,
energy drink too. Like I always drink Celsius. Like whenever I do drink energy drink.
yeah. You want
What's
to
your
see
favorite
it?
flavor?
Well, my friend, she let me try hers. Yeah, I'll show you real quick. I just got
Okay.
it today.
Yeah. Oh my God. You got a whole
The whole
Amazon box
pack.
of Celsius?
Yeah, I got the mango passion fruit.
Mango passion fruit. Oh, what the heck? I never had that before. They don't sell that at school, right? On campus?
They don't. So you have to order on Amazon.
Oh my goodness. Oh my God. I see like your dorm too. Cozy. Looks so cozy.
Oh yeah. I mean, it's a bit messy right now, but yeah, this is gonna be my last year for the dorms, and then I'm gonna get an apartment.
Yes. And so it looks so peaceful studying at night over
Oh yeah,
there.
I even got a sunset lamp.
Oh
Yeah,
yes.
it's pretty nice, pretty chill.
Mm-hmm. That's
But
good.
thank you so much for your help
Yeah.
tonight.
Mhm. Yeah,
Thank
no worries,
you.
Alicia. Hmm.
Okay, I'll see you tomorrow.
Yep, I'll see you tomorrow, Alicia. Bye.
Bye.
Bye.